Hi everyone! This is Professor M Does Science, and today I want to talk about angular momentum in another one of our videos on rigorous quantum mechanics. If you have studied classical mechanics, you will know that angular momentum is a key concept to understand the physics of many systems, so it won't come as a surprise that the same is true for quantum mechanics. For example, angular momentum is absolutely essential to understand the motion of particles in central potentials, an example of which is the all-important hydrogen atom. But angular momentum in quantum mechanics is a lot more general than what you might suspect from classical physics. You might have heard about the spin of quantum particles. Spin is actually just another type of angular momentum. So what we will do today is to motivate the concept of angular momentum in quantum mechanics, and we will also explore how we can generalize these ideas, which will prove really important as we move forward. So let's go! We're going to start with a reminder of angular momentum in classical mechanics. So let's consider some reference point, and for ease of visualization, let's also draw a vertical axis going through that point precisely. If we have a particle here at position r that is moving with momentum p, and again for ease of visualization, we can imagine that it is going around the reference point in a circle, then the angular momentum vector L is the cross product between the position vector r from that reference point and the linear momentum p. And this definition is general, so you should view this drawing as simply an example for clarity. Angular momentum, like position and linear momentum, is a vector quantity. And this means that for calculations, we typically want to write it in terms of components defined with respect to some basis. For example, in Cartesian coordinates, the components would be Lx, Ly, and Lz. But moving forward, we're going to be more general and write these as L1, L2, and L3. We will use the same convention for the position vector, typically given as x, y, z, but we will label them R1, R2, and R3. And similarly for the linear momentum vector. In this notation, we can now carry out this cross product, and we find that L1 is equal to R2P3 minus R3P2, and similarly for the other two components. So what is angular momentum in quantum mechanics? Angular momentum is described by an observable L hat, which is really made of three observables, L1 hat, L2 hat, and L3 hat. In classical physics, angular momentum is a quantity given in terms of position and momentum, so we can straight away use the usual quantization rules to promote these two quantities to the corresponding quantum mechanical operators. This means that we can write L1 as equal to R2P3 minus R3P2, and similarly for L2 and for L3. And we don't have to worry about the order of the terms, because all the products that appear mix position and momentum coordinates along different axes, so they all commute. Now that we have defined the angular momentum operator in quantum mechanics, the very first thing we need to confirm is that it is a Hermitian operator, so that it is unobservable. So let's start by taking the first component L1 as an example. L1 dagger is equal to R2P3 minus R3P2 dagger, which is equal to R2P3 dagger minus R3P2 dagger. Now, remembering that the adjoint of a product of operators reverses their order, we get P3 dagger, R2 dagger, minus P2 dagger, R3 dagger. The momentum operators P are Hermitian, and so are the position operators R. So we get P3R2 minus P2R3. And these two operators commute because momentum and position appear along different axes. So we get R2P3. And similarly, these two operators commute, so we get minus R3P2. And finally, this equals L1. We could repeat the exact same derivation for the other two components, and overall, what we find is that each component is indeed Hermitian. So, in conclusion, the angular momentum components are observables. Let's now look at the commutation relations between the different angular momentum components. And this is going to be a little bit long but really interesting, so bear with me. Let's start with the commutator between L1 and L2. Using the definition of L1, we get this. And then using L2, we get this. And we can expand out the commutator and we obtain these 4 terms. Feel free to pause here for a second to cross-check this, but it should be clear after a moment. The next thing to do is to remember that the position operators commute, the momentum operators also commute, and the position and momentum operators obey the canonical commutation relations. What these operators tell us is that the only non-zero commutators are those that involve mixed position and momentum operators along the same axes. Using these results, we can see straight away that these 2 terms vanish because they only involve position and momentum operators along different axes. Another useful result to remember now is that the commutator of A with a product of 2 operators BC is equal to B times the commutator of A with C plus the commutator of A with B times C. Using this result, we can expand the 2 surviving terms to get these 4 new terms. Again, feel free to pause the video here for a moment to double check this step. Moving forward, the commutators in the first and last term vanish because they don't involve the commutator mixing position and momentum along the same axis. Expanding once more the 2 surviving terms, we get again 4 new terms. And again, you should pause if you want to cross-check this step. That is absolutely fine. You should really convince yourself that this is indeed the result that we get. Moving on, the 2 middle terms vanish. The first term contains the canonical commutation relation in reverse order, so we get minus IH bar. And the last term contains the canonical commutation relation, so we just get IH bar. Let's make some room in this slide and copy the latest result up here so we can continue with our derivation. Right, we can now rearrange it to IH bar multiplying R1P2 minus R2P1. Comparing with the definition of L3 up here, we see that this is in fact equal to IH bar L3. We could repeat the same exercise for the other commutators, and we would find that there are only 2 more commutators that are non-vanishing. The commutator between L2 and L3, which is IH bar L1, and the commutator between L3 and L1, which is IH bar L2. We can write these relations in a more compact form as the commutator of Li with Lj, giving IH bar sum over k of epsilon ijk Lk. In this expression, epsilon ijk is called the levi-civita symbol, sometimes also called the antisymmetric symbol, and it is defined as follows. When the subindices are all different and they appear in the order 1, 2, 3 or any cyclic permutation, then it is equal to 1. If all subindices are different, but they appear in a cycle that does not have the order 1, 2, 3 or a cyclic permutation, then it is equal to -1, and all others vanish. If you have encountered the levi-civita symbol before, fantastic. If not, don't worry. It is simply a convenient way to write our expressions in a more compact form. But you should convince yourself that this compact form is equivalent to these relations up here. A further simplification of the notation is typically used, where we write this expression without explicitly including the summation symbol sigma. This is something called Einstein notation, and in this notation we understand that repeated subindices are summed over. In this example, the subindex k appears in the levi-civita symbol and in the angular momentum component, so this means we have a sum over k. Again, if you encountered Einstein notation before, that's awesome. Otherwise, all you need to remember is that in this shorthand, repeated indices are summed over. Overall, The first time we learn about angular momentum, it may appear tricky to remember all of these commutation relations with all of these different indices. But in reality, it is not so complicated, and with a little practice, it will become effortless. An easy way to remember the commutation relations for angular momentum components is by noting that they obey a cycle 1, 2, 3. In the first one up here, we have 1 here, 2 here, and 3 here. In the second one, we start with 2, then 3, then 1. And in the third, we start with 3, then 1, then 2. So they always appear in the same sequence. The properties of unobservable in quantum mechanics are determined by its commutation relations. And in the case of angular momentum, the commutation relations are the ones up here, where, as a reminder, I am using the Einstein convention, so this should be interpreted as having a sum over the repeated index k. If we forget about the physical meaning of angular momentum for a second, then commutation relations such as these are simply mathematical relations that we can work with in an abstract manner. In this context, we will find that in quantum mechanics there is an observable called spin that obeys the exact same commutation relations as those obeyed by angular momentum, but which crucially has no classical counterpart. But because spin obeys the same commutation relations as the usual angular momentum, it can be understood in very similar terms, so we also call it an angular momentum. In this language, we define a general angular momentum in quantum mechanics as any observable J that is made up of 3 observables J1, J2, and J3 that satisfy these commutation relations. All the properties of the angular momentum J that are a consequence of this set of commutation relations will be true for any physical quantity that obeys them. This will obviously include the usual angular momentum that we have been discussing, which we will sometimes refer to as the orbital angular momentum. When we want to emphasize that we are only discussing orbital angular momentum, we will typically label angular momentum with the letter L, as we've been doing so far. And similarly for the corresponding commutation relations. But we also have this new type of angular momentum that only exists in quantum mechanics, that we call the spin angular momentum. When we want to emphasize that we're discussing spin angular momentum, we will typically label angular momentum with the letter S. And similarly for the commutation relations. So you will see angular momentum labelled by all of L, S, or J. L and S are used when we want to clarify orbital versus spin angular momenta, while J simply refers to a general angular momentum which could be either or a combination of both orbital and spin angular momenta. As an example of using the general angular momentum J and understanding the consequences of the defining commutation relations, let's consider the angular momentum magnitude. As J is a vector operator with 3 components, we can define a magnitude for it as J squared, which is J dot J. In terms of components, this becomes J1 squared plus J2 squared plus J3 squared. This operator is trivially Hermitian because each component Ji is Hermitian. And in turn, this means that J squared is an observable, and we will see in other videos that it plays a major role in the quantum theory of angular momentum. But today, let's simply calculate its commutator with J1. We get these 3 commutators by using the definition of J squared. The first one trivially vanishes because J1 commutes with itself, and for the other 2, we can expand it in the usual way to obtain these 4 terms. Using the defining commutation relations for angular momentum, these 2 commutators are equal to minus IH bar J3, and these 2 commutators are IH bar J2. We can see that this term cancels with this term, and this one with this one, so that the commutator vanishes. We can repeat the same exercise for the other components, and they will vanish. And that's it. We're done. We have defined angular momentum in quantum mechanics as any set of 3 observables that obey these commutation relations. The fact that the components of the angular momentum operator in quantum mechanics don't commute is a rather remarkable result. You will remember from the video on compatible observables that if two observables O1 and O2 don't commute, then we cannot find a common set of eigenstates. You will probably also remember from the videos on measurements that if two observables don't commute, then when we measure one of them, we modify the probability of finding a given outcome when we measure the other. We sometimes describe this feature as saying that we cannot measure two non-commuting observables simultaneously. And you will also remember from the video on the Heisenberg uncertainty principle that if two observables don't commute, then they are subject to an uncertainty principle. As an example, remember the videos on the position and momentum operators, which don't commute with each other. And this means that quantum systems behave in dramatically different ways compared to classical systems. For example, representing a quantum state in the position or momentum representations in terms of the corresponding wave functions, if we have a very narrow wave function in the position representation, then this means that we have a very wide wave function in the momentum representation. And the opposite also happens, and in general, they are related by a Fourier transform. With angular momentum, we are taking this quantum weirdness one step further. It isn't two different quantities like position and momentum that don't commute, but instead it is the different components of the same quantity, angular momentum, that don't commute. This makes the theory of angular momentum in quantum mechanics extremely rich. Intriguingly, we have found, if you remember in the previous slide, that J squared does commute with each of the angular momentum components. You should remember this result, because it'll prove useful as we learn more about the topic, and we'll just leave it here for now. Angular momentum in quantum mechanics is not restricted to orbital angular momentum. Instead, we can define a general angular momentum J that includes the orbital angular momentum, but it can also include other types of physics. So check out our other videos to find out more about orbital angular momentum, spin, and mixed angular momenta. And as always, if you liked the video, please subscribe.